All right, welcome to CSE 215. So, my name's Nick. If you haven't had me before, I'm your teacher. Most people here. Hello. I am not grading you based on attendance, but I'm going to pass around a sign-in sheet. If your name's not on there, put your name on the bottom, and we'll have to figure out why you're not on there, because that's the list I had from Canvas as of yesterday. So everybody should be listed there.
Where are those dudes on the card?
Say again?
Where are those dudes on the 215?
Who are those dudes on the 215 page? Any ideas?
Einstein. Neil Armstrong and Roosevelt.
Good guess.
Johnny Depp and Einstein.
Even better guess. So that is Einstein on the right. Person on the left, his name is Kurt Gödel. A mathematician from the 20s, the other 20s. And we will talk about what Kurt Gödel did for the world. He threw a big monkey wrench in a lot of what people thought they knew about the universe.
A monkey wrench?
A monkey wrench?
Oh.
It's an expression.
Oh. I was way more just like a monkey wrench.
All right. So I'm going to run through a few things pretty quickly in here. I'm going to go through the syllabus very quickly. I'll go through the additional policies in a little more detail and talk about the rest of what's on Canvas, and then we're going to jump into talking about discrete structures. Well, let's start with the syllabus. So this is CSE 215, discrete structures. Discrete structures are kind of the math and logic and theory that sort of underpin computer science, right? We do computer science, we write programs, we write if statements and loops and things like that. But there's a lot more going on. Computer science is really an outbranch of mathematics in a lot of ways. And we write programs, but how do we know those programs are correct? Right? We run it in a test case and it looks fine, but you turn it in and you lose a bunch of points because there was another case you didn't check. How do you know your program is doing what it's supposed to do without checking it for every possible input? This is a question in logic and mathematics and philosophy in some sense. And this course really touches on a lot of different areas, including logic, propositional calculus, theorem proving, mathematics in a variety of different ways, set theory, functions, things that border on what we might call topology, and computer science, right, ties it all together. So this course is really geared to help you with CSE 222. So usually you take this course either in fall or in winter, which means right before or during CSE 222. CSE 222 data structures depend a lot on what we call recursion. And recursion is an outbranch of something that we call mathematical induction, which is one of the big concepts we learn in CSE 215. Recursion is a wonderful tool that in some introductory computer science classes, recursion is taught for that first course, and you typically see drop rates of around 50%, people who switch to something other than computer science, because it's kind of a daunting concept for somebody who's new to programming. At this point where you're proficient in C and we're starting to learn data structures, right, that's a really nice entry point for concepts of recursion. And this course sort of builds some of the theoretical foundation that we need for that. So we'll talk a lot about computer science in here. We'll talk some about this stuff in Computer Science 222. So my name's Nick. My email is the best way to reach me. Do not try to reach me through email on Canvas. It will bounce back with a message saying send me email like this, because Canvas email is hit and miss sometimes. My office is 115. It's the other side of the collaboratorium. I have hours posted on the website. There's also a copy of those on my door. But basically, Mondays 8 to 9, Tuesdays 7:30 to 9, Monday, Wednesday, Friday 12 to 12:30. That's right before here, which is why I came in late. And Friday afternoons at 2, which is right after this class. So different times throughout the week, different times of the day, hopefully something in there works. The main text for the course is an open access PDF, so you can download that for free. It covers some things we don't go into, and we also cover some things that are not in that text. But it's a pretty good coverage. I'll assign homework questions from there, so you definitely want to download a copy of it from that link. There are different versions of this around, so if you just grab text by title, you might get a different version with different questions in it. So this is a link that should take you to the copy that we're using. And there's some of the things that we'll be talking about: functions, relations, probability, counting, propositional logic, predicate logic, formal proofs, all kinds of impressive sounding things, including theories of computation, which will be relevant. The schedule is pretty close to approximately true-ish, but maybe not. So this is the set of things that we'll cover, but we might do them in a different order. We'll definitely start off with propositional logic, though, and then who knows after that. But week 1 should be pretty close to reality. All right, grading for the course. You'll have a homework set every week, probably not this week, but starting next week. I'll give you a series of questions to write up, and I will generally grade 1 problem from the set. And then the total homework grade is 15% of your course grade. I'll give you a few quizzes during the term. They'll be about 30, 45-minute in-class tests of what we've been doing more recently. Those are a total of 15%. You'll have 2 programming assignments, which you can do in C or C++. I'm not really picky. Total of 10%. And those are just a chance to sort of tie in some of the things we're talking about in here with some actual code that you can develop. So just helping to make that bridge. And then midterm exam, 25%, comprehensive final, 35%. So pretty straightforward grading. Support services, I'll let you read this in detail on your own, but basically if you're in a situation where you feel like some kind of accommodation would be helpful for you, talk to me, talk to the ESS office, come by and see me, shoot me an email, something, okay? What are accommodations? Accommodations are things like, I have difficulty seeing unless I'm in the front row, right? We can arrange to have a seat in the front row reserved for you. I have difficulty taking notes while paying attention. You can get a note taker to take notes for you. I have test-taking anxiety. I would do better if I had time and a half on the tests, or if I had a low distraction environment, right? All these kinds of accommodations can be made available to you. There's a whole support office, DSS, for handling these kinds of situations. So please take advantage of that if you feel like some sort of accommodation would be helpful. College-wide policies, I'll let you read this yourself also, but basically the punchline here is we want to treat people with respect. We want to treat people equally. There's 0 tolerance for discrimination, discriminatory behavior, okay? If you see something going on, if something is going on with you, come and say something, okay? Talk to me, talk to another teacher, something, because it's something that Clark takes extremely seriously, and we want people to be able to concentrate on, learning their class material, getting their work done, being successful during their time here at Clark, not dealing with, people being weird. So come and talk to me or somebody about that. Code of student conduct is boilerplate. You can read that. Engineering, computer science course policies. This is the same for every course. So look through those. Let me know if you have any questions about them. So that's the syllabus for the course. The additional course policies take precedence if there's a conflict between what these things say. So meeting times, Monday, Wednesday, Friday, 12:30 to 1:55, except Mondays I have to teach at 2, so we'll probably end at 1:50 on Mondays. Instructor, that's me again. Office hours, office is 1:15. There's a Discord server set up for this course, also for 222. I forgot to mention that last time. If you like Discord, feel free to hop on there. People talk about whatever. talk about course material or questions on the subject or just anything in particular. Assessment, hopefully this is what I just said. 15, 15, 10, 25, 35 sounds right. Keys to success. So I hope this will be a fairly interactive class, and a fair amount of class time will be spent with you working on the board or at your desk in groups going over concepts that we've been discussing. So we'll talk about an idea, and then I'll present some problems, and you'll work in groups at the board on these problems, right? So it'll be like sort of practice on your homework questions. We're working in a group where I can walk around and see what people are doing, give you some feedback, and so on and so forth. So you really want to come to class, okay? Because if you miss out on that, you miss out on a key learning opportunity. And if you're trying to prove something using mathematical induction, and the first time you try to do it is during the midterm, it's not going to be a good experience, okay? If you're working on the board with 2 or 3 friends trying to do mathematical induction, and I can come by and see what you're doing and give you some advice, and then we can do that a few times, and then you can work on some homework problems a few times. Then when you get to the midterm and there's a question that says use mathematical induction to prove the following, it's old hat, right? You've done it before, it's not a big deal, right? That's the situation you want to be in. So that the exams are not a learning experience, they're just demonstrating what you already know how to do. So class time is going to be really important in that way. Try to use the class time to learn the material. Okay, I record the lectures, I post the link to the YouTube channel on Canvas, so you can go back and you can see everything that I've written and you can hear everything that I've said through the recording. So you don't need to write down everything that's happening in here. What you really want to do is think about the concepts that we're discussing, right? And when I ask a question, think about that, and if questions come up in response to that, ask those questions in class. Okay, that's what we're here for, really, is to expose questions and talk about them and have it be a learning experience. Not just for me to stand up here and spew out information that you write down furiously. Try to avoid getting too distracted in class. We talk about a lot of different things. We get into a lot of really, really fun topics. If I mention something like, you know, if you can solve this problem, it's worth $1 million, right? Don't go down a Wikipedia rabbit hole right then and there. Write a little note to yourself saying, check out the Millennial Prize, you know, and then later on, go ahead to Wikipedia and go down that rabbit hole. But try to stay present as much as possible during lecture. It's an hour-and-a-half class. It's a long time, okay? But try to stay here. If you drift off, and you notice that if you drifted off, just bring yourself back. Don't beat yourself up over it. Just try to stay present as much as possible. All right, exams and quizzes, closed book, open note, 4 double-sided pages allowed. That should be plenty for this course. There's not a lot of memorization involved. It's really learning how to apply a small number of things. No late work, so well, you can ask, but there's no point in asking. So homeworks and quizzes and things like that, they got to be done on time. Programming assignments, make sure you write the code yourself. You can look up help with algorithms, but your best bet if you're stuck on the programming questions is come and ask. Okay, ask me. Don't ask somebody else, because other people may give you their code, which gets you both in trouble for plagiarism, or they may tell you something really cool that they know about how to do this, which is like, you know, a senior level concept, and now you're going to be trying to figure out this thing that you're not really supposed to learn for another few years. So come and talk to me, right, pretty quickly if you feel like you're stuck on something. I'll try to direct you in the right way. There's a Linux server that we use for the CS sequence 224, 222. If you're taking 222 right now, or you took 224 in fall, you should have an account on there. If you don't, let me know as soon as possible, because you need to use this machine to do your programming assignments, because that's the system I'm going to test them on. So check that out and send me an email or come and see me during office hours. And I'm not going to get brutal about programming style, but develop a programming style. Indent code, use reasonable variable names, put comments in your code, things like that. This is not a programming course, okay? This is much more about logic and theory, but there are a couple of programs you'll do. and I'm not as brutal in grading those as I am in, say, 222. But you know, just keep in mind your programming style. Okay, that's it for the specific stuff. So textbook is also available here. There's an additional 215 text which covers some of the material that's not in the main text. So that's also an open source textbook, so you can use that. There's a link to the lecture videos on YouTube. There's a link to the Discord server invite.
Is the Discord server the same one that we had last
It's the same one, yeah. Yeah. It's the same 215 channel, and I made a new 222 channel, so, but whatever. All right, so the quizzes are done in class. They're not Canvas quizzes. 2 programming assignments, midterm and final. So, homework. So your first homework will be due on the 15th, which is a ways away. So I'll probably post something Wednesday. I'll give you a week for homework 1, but we got to see where we get to. What I want to talk about, though, is this guide for writing up homework. So this I am going to be very picky about, because I get some really interesting homework submissions. And it actually becomes a challenge to grade them sometimes. So I implemented this last quarter, and it actually worked really well. And I swear people did better on their homework by paying more attention to how they wrote it up. So basic guidelines. Homework should be done neatly. Okay, if you need to cross something out, put a single line through it. Don't scribble things out. But ideally, especially with the more complex problems, work them out first on scratch paper, on a whiteboard, something. And then once you have the solution, write that up neatly to turn in. Okay? This has the advantage of, one, you're actually, you know, you're working out the problem, but once you have the solution, by actually writing it out by hand, that helps sort of reinforce it in your brain. Right? It's like a muscle memory kind of thing, dual modes. But if you're really confident that you can get it worked out, you know, neatly the first time, you can do that. Use a number 2 pencil or some other lead that makes dark lines. Occasionally I get these lines that are like really difficult to read, and you know, I gotta shine the bright light on it and squint. And, so make it easy to read. Work in pencil. Okay. Find a pencil that works for you. You can do a plain old number 2 that you just sharpen in the wall, or you can get a mechanical pencil, but something that you can erase easily really helps. Okay, especially with this subject, because there's a lot of room for making mistakes when you write. Do your printing neatly. Okay, avoid longhand unless you have exceptionally beautiful cursive handwriting. Paper 8.5 by 11, please. Okay, standard letter size US. I would prefer not to see, you know, 8.25 by 10 3/4. It sounds picky, but it really makes a difference when I'm managing a stack of 30 homework problems. If one of them is slightly bigger or smaller, it gets caught. In other assignments, it gets lost, things like that. Clean edges. Okay, if you're ripping from a spiral notebook, hopefully it's got a perforation on the edge, or cut it or something, or just get plain paper. I'm kind of geeky about writing, but when I was in school, I liked using plain white paper and putting a piece of graph paper underneath it, so I could see lines and write, you know, horizontally. But then I'd have just plain paper. That's fine if you like. You can also use standard engineering paper, the green stuff with graph paper on the back and lines on the front. That's fine. Do your problems in order. Okay. So if you're supposed to do problems 3, 5, 7, 8, and 9. 3, 5, 7, 8, and 9, not 3, 9, 7, 5, 8. Okay, sounds silly, but again, I mean, I've gotten so many variations of this. All these things are in response to things that I've gotten in the past. I'm going to ask you to do single-sided only. Okay, hopefully we recycle paper, but just use the front of each page. Don't go onto the back. Page layout. Top of the page, staple in the upper left corner. Your full name, no initials. Middle name you can initial, but full first name, full last name, in that order. CSE 215, the homework number, the date, and then the page number, like 1/5, 2/5. Okay. And that's what all of that spells out. And then work from top to bottom. Okay, so start at the top of the page, write the problem number in the column in the margin, and start working out the problem. Okay, don't draw an arrow that goes back up to the middle of the page and continues from there, and then an arrow that goes over sideways. Strictly top to bottom. If you get to the bottom and you're not done, go on to the next page. Okay, your teachers will love you if you get into this habit. Right, any class that you're turning in homework in, your teachers will totally love you for this. Because there's no? In what way?
I don't know.
Like yeah, they will. All right, and then at the end of your work, when you get down to an answer, circle it. Okay, so that it's clear what the actual answer is. And if there's multiple parts, if there's 2A, 2B, 2C, right? In the margin, say 2A, work out 2A, circle the answer. 2B, work out 2B, circle the answer, and so on. The whole point of all this is it should read like a book when I get to your homework, right? I shouldn't have to flip around from page to page and go upside down and remove the staple so I can look under the corner to see where the answer is and things like that. Okay, make it easy for whoever's grading it to follow your work, and it really helps with partial credit, right? If you get down to the answer and the answer is supposed to be 25 and your answer is -2, if I can't follow your work, you got 0 points, right? If I can follow your work and say, oh, you know, you multiplied 5 times 6 and you wrote 40 instead of 30, but everything before that was fine, everything after that's fine, you'll probably get full credit, you know, because I don't care if you can't multiply, as long as you apply the technique correctly. So this really helps for partial credit too. All right, so that's available on Canvas. And the first homework, I'll be a little bit more forgiving. Okay, I'll give you lots of feedback. And then starting with homework 2, I'll just kind of expect you to follow that.
With the homework problems, will we know, do we have access to like an answer key so we can see what answer we should be arriving at?
So I believe it's odd numbered questions have answers in the back of the book.
Okay.
And sometimes I'll put in some odd numbered ones. And then I'll grade one of the even numbered ones. But often I'll just have even numbered ones, but you can try the odd numbered ones close to the ones I assigned. And if I post the homework by Wednesday, right, you can look at it and you can, you know, we'll talk about it in class, and you can work on it and try to have it done by Friday. And then if there's things you don't know how to do, you can ask about it on Friday, and we can discuss it and so on, right? But the earlier you try your homework, the more chance you have to talk about it in class and, you know, figure out how to do something you didn't know how to do. If you don't start it until the day before it's due, right, then there's no class time to address your questions. And then you're kind of at the mercy of, you know, maybe Discord or an email to me or something. So definitely want to start homework early when possible. All right, any questions on any of that? So last thing I want to talk about is this possibility of a strike next week. So I'll talk about this more on Friday if things have not been resolved, because it's all speculation until then. But basically, if teachers go on strike next week, it'll basically be like hitting a pause button on the course. Okay, so if there was homework that was due on Wednesday and we don't have class Monday, then, you know, things will get pushed back accordingly. The intent is that any time that's missed because of the strike will be made up somewhere. I don't know what the plan is for that. But all sides, right, our primary concern is students, right, and making sure that you get what you need out of this course. My primary concern when I'm teaching is trying to prepare you to transfer to a university. That's really what my goal is. And whatever it takes to make that happen, right, we will make that happen. So if there's a strike next week, things will basically get paused, and we'll continue once things are resolved. But Friday, we should have a good idea if this is going to happen or not, and if it looks like it's going to, then we'll talk a little more about specifics on Friday. But it will work out one way or another in the end. All right, so if you came in late, add your name to that before you leave today. So let's talk about discrete structures. And like I said, this course covers a lot of things. It covers some computer science, some mathematics, some logic, some philosophy, and sort of how all these things relate together. We're going to begin with something called propositional logic. You can call this propositional calculus if you want to sound even more impressive. Calculus just means reckoning, calculating. So propositional logic, well, not surprisingly, it's built on the idea of a proposition. And this is possibly the most important definition you're going to get for this part of the course. So a proposition is a declarative statement that is true or false. Now that's a pretty easy definition, but it's a really important one. A proposition is a declarative statement that is either true or false. So some examples of things that are propositions. My name is Nick. That is a declarative statement. I'm making a declaration. I am stating that my name is Nick. And that has a truth value. It happens to be true. 1 + 1 = 5. That is also a declaration. I am stating that if you take 1 and you add 1 to it, you end up with the value 5. Happens to be a false statement, but it's still a declarative statement. So that is a proposition. This is CSE 215. That's a proposition. This is a prerequisite for basket weaving 200. That's a proposition. Things that are not propositions. X + 1. Now that's an arithmetic expression which says take the value of x and increase it by 1. It's a valid mathematical expression, but it's not a proposition.
So would just 1 + 1 be not a proposition as well?
1 + 1 is not a proposition. 1 + 1 = 2 is a proposition. But this does not have a truth value. Who are you? Not a declaration, not a proposition. Go eat, not a declaration. If x is greater than 5, then x squared is greater than 25. That is a proposition. If x is greater than 5, it's not a proposition. So pretty easy, other than the weirdness of human language, which we'll bump into a lot, pretty easy to look at something and say, is this making a declaration? Well, no, this is saying if x is bigger than 5. It's not even a sentence, right? But this is clearly stating, if x is bigger than 5, then x squared is bigger than 25. That's a declaration. And it might be true, it might not be true. Doesn't matter. Okay, so propositions, not propositions. And the reason that this is so important is that when we start talking about making formal proofs, a proof is going to be a series of propositions, each following from things that we've already stated. And it's really, really common when somebody's writing a proof that they end up writing something like this or this. And since those are not propositions, you've no longer got a valid proof. And a lot of times you'll write up a proof and I'll give it back to you and I'll circle something and it'll say not a proposition. Okay, that's what's going on here. Every line of a proof has got to be some sort of declarative statement. And in a proof, normally there are declarative statements that are true, right? And then every statement that you write is true, and eventually if you can write the thing you're trying to show, then you've got a proof. We'll talk a lot more about proofs in a few days. Okay, but this is why propositions are so important. All right, so we'll talk about propositional variables. So a propositional variable is just a letter that represents a proposition. It's a letter that stands for a proposition. For example, let P be the proposition two is bigger than 1. So 2 is bigger than 1, that's a proposition. It's a declarative statement with a truth value. I'm using P as a variable that represents this proposition. Okay, it's just like a variable in a program. It's a placeholder for this statement. And we have a couple of letters that we use in very particular ways, namely T and F. T is a symbol for true and F is a value for false. So if we have a proposition, it's got a truth value, right? If that proposition is true, we can use the symbol T to say it's true and F to say it's false. So those are called truth values. And so this is developing something we can call propositional calculus. So how old is this stuff? How long have people been studying?
At least 3 years.
At least 3 years. Excellent.
7 years.
7 years.
2000.
2,000 years.
Is it Aristotelian? Is that the origin of it?
It is. So Aristotle was
like
studying this
12
stuff.
years ago, right?
So this is circa 300 BC. So 2,300 years. So yeah.
I said 12, that's close.
Yeah. So Aristotle, right? Why were people studying propositional logic 2,000 years ago? Well, this is a fascinating area because, humans have this way of thinking, of drawing conclusions from things that we know, right? If I drop that rock on my foot, it will hurt, right? We observe this, and now I conclude that if I drop this rock on your foot will hurt, right? And if I'm trying to hurt your foot, I might go over and drop a rock on it, right? how do we know that? Well, it's propositional logic in some sense, right? So we have this ability to think about things abstractly. Abstraction is one of the sort of real special aspects of intelligence. And so people have been fascinated with this for a long time and have tried to formalize this notion of how we think logically. And George Boole, 1854, modernized this, right? So this is where Boolean algebra, Boolean logic comes from. It was George Boole, so mid-1800s. And here's the real cool part about all of this propositional logic. You can make new propositions from old ones. And we don't always think of it like that, but this is what we're doing when we do things like Boolean algebra. So for example, let P be a proposition. And it could be any proposition. 1 + 1 = 2. My name is Barbara. I have a cat that can fly. It could be any proposition, okay? If P is a proposition, we can write the following. This funny horizontal bar with a hook, followed by the letter P. This is another proposition. And it's called not P. Or it's sometimes called the negation of P. So let P, or let Q be the proposition. It's rainy. Then not Q is the proposition. It's not rainy. Technically, it's the proposition, not it's rainy, but we don't talk that way usually. But this gets into this weirdness of human language. Human language is more comfortable to us, but less precise than propositional language. And so we need to sort of like bridge this gap sometimes between the strict formalism of propositional logic and the conventions of spoken or written language.
Is there a technical term for the like weird bar?
For the what?
The weird bar?
That's just a negation symbol. It's probably got a fancy Latin name, but I don't know what it is. We can make up a name, yeah. But PL1 uses it as part of its language. So pops up in some programming languages. So Q is a proposition, not Q is the negation of it. So if Q is the proposition, it's rainy, not Q is the proposition, not it's rainy. Okay? So if it's actually rainy, then Q is true, not Q is false. Okay, and if it's not rainy, then Q is false and not Q is true. And we might be tempted to say, you know, not Q is the proposition that it's sunny, but we know that's not necessarily the same as it's not rainy. Because there's lots of days it's not rainy, but it's also not sunny. So we've got to be a little careful with written language. It can be imprecise, but usually we know what's going on, and if we're not sure, it's a good time to ask, like especially during a test or something. All right, so this funny bar means negation. And if we want to describe the behavior of this, we can do this with something we can call a truth table. So here's what negation does. So suppose P is some proposition whose truth value is true. Then not P will be a proposition whose truth value is false. And if P is a proposition whose truth value is false, not P will be a proposition whose truth value is true. And since we know a proposition is either true or false, this table covers every possible proposition state. Whatever P is, whatever crazy proposition it might be, it's either true or false, and this table tells you the corresponding truth value of not P. So that's a truth table, and it's an engineering 250 type truth table. T and F instead of 1 and 0, but the same concept. And so given one proposition, we create a new proposition. So let P and Q be any two propositions. We can create a new proposition called conjunction, which is P and then this caret and Q. That's a new proposition. And we can also think of this as being the AND operator. So if P is a proposition and Q is a proposition, the conjunction of PQ is the statement P and Q. So let P be the proposition, it is rainy. Let Q be the proposition, it is Monday. So P conjunction Q is the following. It is rainy and it is Monday. And we can define the behavior of this with a truth table. And we can probably guess how to fill this in. If P and Q are both false, then the AND of P and Q is certainly false. And if P is false, even though Q is true, P and Q together will be false, because the AND is saying P is true and Q is true. So if they're true and false, that'll be false. The only time P and Q is true is if P is true and Q is true. That's what AND means. All right, well, we can also do the disjunction, which we write with this upside down caret, or a V. And logically, that's an OR. And a disjunction is true if either P or Q is true, or both. So P could be the proposition it is sunny, Q could be the proposition it is Monday. The conjunction would be false, because it's not sunny. But the disjunction would be true, because the disjunction says it's sunny or it's Monday. And since today is Monday, that disjunction is true. So there's the truth table for an OR. And we don't usually talk about this too much. But there's also an exclusive OR. Which is the plus sign in the circle. And it's kind of like a disjunction, except it requires that one of those propositions is true and the other is false. That actually doesn't pop up a whole lot in logic. So this looks a little familiar, right? Right, we've seen this in Engineering 250.
Like we have new symbol, and then exclusive or is just.
Exclusive OR is just the same. There's probably a fancy symbol for it that I've just never encountered. And we can start to talk about things like the fact that P ORed with Q is exactly the same as Q ORed with P. And what do I mean by exactly the same? Well, the statement, it is sunny or it is Monday, is not exactly the same as the statement, it is Monday or it is sunny, right? Because we got things in a different order. But logically, as propositions, the truth values of those two statements are the same. That's really what I mean here. And sometimes you see this with a three-lined equal sign, which we can think of as logical or logically equivalent. Even though the statements themselves sound different, the two statements are simultaneously either true or false. They always have the same value, whatever the values of P and Q are. So they're logically equivalent. So we have all kinds of facts like P or Q is logically equivalent to Q or P. Right? That's called commutativity. It means you can do things in different orders. Right? So conjunction is also commutative. We can do the ands in either order. We also have associativity. Q ORed with R, and then ORed with P is the same as P ORed with Q, and then ORed with R. So this is commutative. This is associative. And the same if we use conjunctions instead of disjunctions. So the order of doing AND operations doesn't matter. If we negate the negation of P, we get P. So if P is the proposition that it's sunny, not P is the proposition that it's not sunny. Not P is the proposition that it's not sunny, which is the same as saying that it's sunny. And this is where spoken language starts to fail us. But this is double negation. And we've seen all of these things before also, right? This is just commutativity and associativity of ands and ors, right? Pluses and dots. This is double negation. Variable with a bar on top with another bar on top of that is the same as the original variable. There's a distributive property. P ORed with the quantity Q and R is the same as P or Q ANDed with P or R. And we'll go through these in more detail later, and I'll actually give you a handout that has all of these things on here, but just giving you a flavor. What is this one? Not quite. You got the first letter right, though. I'm going to bring in a wad of SpongeBob money and hand out like $1 million crab bills. Think Engineering 250.
It's the negation of the conjunction of P and Q.
Mm-hmm. We had a name for this. De Morgan's. Don't forget De Morgan. And it's got a parallel version or a dual version. right, so if you want to switch from disjunction to conjunction, you can do that by moving the negation inside each term, and vice versa. So all these things carry over from Engineering 250 to propositional logic. When we start talking about set theory in a few weeks, we'll see all these things again in the language of set theory. It's one of these things that cuts across disciplines, it just pops up again and again and again. And you can study these things in the abstract. You can go way off the deep end and study something called category theory, which is like abstract study of nothing, and it's glorious. But we see these things popping up, right? So we'll be using these things to do mathematical proofs, for example, by changing things from one form to another. All right, let's go back to making new propositions from old. So let P and Q again be propositions. We can write P arrow Q is the proposition if P, then Q. So if P and Q are propositions, we can write a third proposition in the form if P, then Q. And this P is called the hypothesis, and the Q is called the conclusion. So let P be the proposition, it is sunny. Let Q be the proposition, I am out for a run. So what is the proposition P arrow Q saying? If it is sunny, then I am out for a run. We can really just take the word if, tack on P, take the word then, tack on Q. If it is sunny, then I am out for a run. So this is if P, then Q. And there are other ways we can write this conditional statement. Sometimes you'll see it written if P, comma, Q. If it is sunny, comma, I am out for a run. And the then is understood. That's kind of sloppy, but it's something we do in written or spoken. P is sufficient for Q. It is sunny is sufficient for I am out on a run.
So in this case, you wouldn't be able to switch P and Q and come up with the same thing?
That's correct.
Okay.
Yeah, that's coming up next.
Oh, okay.
Cool. Q if P. I am out for a run if it is sunny. That's the same statement as if it is sunny, I am out for a run. It's just a kind of quirky way of phrasing it. I am out for a run if it is sunny. Q unless not P. I am out for a run unless it is not sunny. Now I might still be out for a run if it's not sunny. This is saying I will tell you absolutely I am out for a run unless it's not sunny. And then I'm not going to make that statement. It might still be true, but I can't make that statement and say it's absolutely true. Okay, so this is equivalent to if P then Q. A necessary condition for P is Q. P only if Q. Q follows from P. A sufficient condition for Q is P. There's a whole bunch of ways of wording this, and they're all fairly confusing. But mostly we'll stick with if P then Q. Well, let's look at the truth table for a conditional. So a general comment about this course, a lot of what we're going to do in this course is going to involve starting with something that we understand, something that we've encountered every day for our whole lives, like if-then, right? We've been dealing with if-thens for a long time, or counting. 1, 2, 3, 4, 5, 6, 7, 8, 9 people in the second row. Right? Things that we understand fairly well, but we're going to work with them in ways that take us into really quirky aspects of something that we thought we understood, but we maybe don't. And we're going to sort of rip apart our grasp on a nice, clean, well-ordered universe again and again. Okay, it's going to be a recurring theme in this course. And so in that spirit, let's do a truth table for a conditional statement, and this will be a little weird. All right, if P then Q. Well, suppose P is true and Q is true in this last row down here. And I make the statement, if P is true, then Q is true. Well, if P is true and Q is true, this conditional is absolutely true. Agreed?
Yes.
Right, so this is certainly true. Okay, suppose that P is a true proposition and Q is a false proposition. So let's say P is 1 plus 1 equals 2, and Q is 2 plus 2 equals 5. Okay, so P is true and Q is false. This conditional statement says if 1 plus 1 equals 2, then 2 plus 2 equals 5. Is that conditional statement true or false? That's definitely false, because 1 plus 1 does equal 2, and that conditional says if this is true, then this must also be true, but that's false. Q is false. So this conditional is definitely false in this case. Okay, suppose P is the proposition 1 plus 1 equals 3, and Q is the proposition 2 plus 2 equals 4. So we're in the case where P is false and Q is true. This says if 1 plus 1 equals 3, then 2 plus 2 equals 4. That's a declarative statement. Is that statement that I just circled a true statement or a false statement?
True.
How many people say true? How many people say false? So logically this is confusing, right? It's saying if 1 plus 1 is 3, then 2 plus 2 is 4. Well, 1 plus 1 is not 3, so what are we supposed to do with this? But the reality is 2 plus 2 is equal to 4, right? This is always true. Even if 1 plus 1 doesn't happen to be equal to 3, that doesn't stop 2 plus 2 from being equal to 4, right? In some crazy universe, maybe 1 plus 1 would be equal to 3, right? Or maybe in our universe 1 plus 1 is not equal to 3, but regardless, the then part is true. Right? But given that this is never true, if we claim that this statement is true, there's no counterexample, there's no condition under which, 1 plus 1 is 3 and 2 plus 2 is not 4. So I'll ask you for a moment to just sit with the idea that this proposition is true. Okay, so let's look at the weirdest case. If 1 plus 1 equals 3, then 2 plus 2 equals 5. So now P and Q are both false. If 1 plus 1 equals 3, then 2 plus 2 equals 5. So how many people think that proposition that's circled is true? And how many think it's false? And how many are not voting? And how many are not raising their hand at all? Okay, this is going to turn out to be true. And that's pretty weird. This says, if I am the Queen of England, then I am rich. Well, I'm not the Queen of England and I'm not rich. But that conditional statement is still considered to be true. And so this is the truth table for a conditional, and it's true in every case except when the hypothesis is true and the conclusion is false. Let me give you a different pair of propositions that may help you feel like this is not as bizarre as it looks. So let P be the proposition x is bigger than 10, and let Q be the proposition x is bigger than 5. This is for some particular value of x. So P arrow Q is the proposition, if x is bigger than 10, then x is bigger than 5. Do we all believe that this statement is a true statement regardless of the value of x? If x is bigger than 10, then x is bigger than 5? Right? That's absolutely true. That's the way that integers work. If an integer is bigger than 10, it's got to be bigger than 5. So this statement should always be true. Now suppose I let x equals 0. So is x bigger than 10? Is x bigger than 5? So P and Q are both false, but P arrow Q is still true. And if I let x equal 7, it's not bigger than 10, so P is false. It's bigger than 5, so Q is true, and P arrow Q is true. And if I let x equal 25, it's bigger than 10, so P is true. It's bigger than 5, so Q is true, and P arrow Q is still true. So those particular propositions at least give you a case where these three rows might feel a little more plausible. Now this third row is an oddball. Guess what? I can't find a value x for which P is true and Q is false. Right? Because to find such an x would mean my x was bigger than 10 but not bigger than 5, and I don't have such an x. If I did, then P arrow Q would have to be false, but we've already decided P arrow Q is always true. That tells me I'm never going to find an x that causes this row to be applicable. So that's a different way to think about it. But if it's not clicking for you, right, I'm going to ask you for now to just sort of accept this as the truth table for a conditional, and we'll work with this and use it in this form. But eventually, you drink enough Kool-Aid, it makes sense. But this can lead to all kinds of weird statements. Like if 1 plus 1 equals 3, then elephants can fly. Well, this is a true statement, according to propositional logic.
So essentially you're saying if you say something false, everything is true.
Everything is true, exactly, yeah. But this is a hard one to convince your friends of. But if you like ruffling their feathers, it's a good starting point. All right, so P arrow Q says if P, then Q. So back to switching the order of these things, Q arrow P says if Q, then P. This is called the converse. Converse, you're just switching the role of P and Q, or if you like, you're flipping the arrow around. If we keep the order the same, but we negate both sides, if not P, then not Q, that's called the inverse. And if we do both, if we say not Q implies not P, that's called the contrapositive. Whoa, indeed. So we have converse, inverse, and contrapositive. So let P be the proposition I win the lottery. Let Q be the proposition I eat a big dinner. So P arrow Q, if P then Q says, if I win the lottery, then I eat a big dinner. And that's probably a true statement, because I would celebrate and I'd invite some friends out and we'd eat a lot of food, because that's what you do. What does Q arrow P say?
If I win the lottery, I eat a big dinner.
That's P arrow Q. What about Q arrow P?
If you eat a big dinner, you win the lottery.
If I eat a big dinner, then I win the lottery. Is that a true statement?
Wish it was.
Could be.
It would be a nice formula. Just go out and eat a big Burgerville dinner or something, and bingo, you got the winning lottery ticket. Doesn't really work, right? So P arrow Q, that could be considered a true statement, right? Q arrow P is not true. I mean, it might be, but it's not logically equivalent. So the converse is not equivalent to the original statement. What about not P implies not Q? If I do not win the lottery, then I do not eat a big dinner. Is that logically true?
Yeah.
I might eat a big dinner every night regardless of the lottery.
But you wouldn't be financially stable.
But that's why I play the lottery. So this is not logically equivalent to if P then Q. So the converse and the inverse are not the same as the original. But the contrapositive, if I do not, this is worth writing out, if I do not eat a big dinner, then I did not win the lottery. I'm playing around with tense a little bit, don't worry about it. If I do not eat a big dinner, then I did not win the lottery. Is that a true statement? Assuming that this original statement was true.
Yes.
It's exactly the same as the original statement. The original statement says, if I win the lottery, I'm going to eat a big dinner. This says if I did not eat a big dinner, then I did not win the lottery. Well, that's exactly true. Because guess what? If I did win the lottery, I would have eaten a big dinner. So if I didn't, must be that I did not win the lottery. And the contrapositive is always logically equivalent to the original implication.
Does the original have a fancy name?
No. I could say, like, let X be the proposition if P then Q. And then I could say the contrapositive of X is equivalent to X. All right, these are important distinctions. And they're distinctions that sometimes humans fail to understand. And it leads to all kinds of problems, sometimes violently and at a national level. So converse and inverse are not the same. So for example, if you are an armed robber, then you own a gun, right? That's pretty safely, if you're a decent armed robber, you own a gun.
Robert, you have arms.
You have arms, right? Okay, what's the converse? If you own a gun, then you are an armed robber, right? It's not logically equivalent. But people will make these kinds of logical missteps all the time. But you can say if you don't own a gun, then you're not an armed robber, right? Or not a very good one, at least. Don't have arms. Yeah.
Can you show the page with the contrapositive stuff real quick again?
That one?
Yeah.
Yeah.
Cool, thank you.
Mm-hmm. All right, so if P then Q and if Q then P. So this is called a biconditional.
Professor,
Yeah,
the name for the arrow, is that just a condition?
that's a conditional, yeah, or an implication or an if then.
All right, thanks.
So a biconditional says if P then Q and also if Q then P. It says that both of these things are true. There's an and in between. And we can write this more succinctly with just a double-headed arrow. So if P then Q and if Q then P.
Is that an if and only if?
That's an if and only if. So P if Q and P only if Q. We could also say Q if and only if P. We could also say Q is necessary and sufficient for P. Or we could say P is necessary and sufficient for Q. What?
Well, what does sufficient mean again?
It means that it's enough to say that P is true. If Q is true, that's all we need to say P is true. But we also need that Q is true in order to say P is true. And this if and only if we have a symbol for, which is just IFF. So IFF means if and only if. So if you eat your dinner, then you can have dessert. Well, chances are this is really a biconditional. It's really saying if and only if you eat your dinner, then you can have dessert. Right? If a parent tells a child this, they usually don't mean you can have dessert anyway. Right? It's really an if and only if. Like if and only if you eat your dinner, then you can have your dessert. If you don't eat your meat, somebody say it.
You can have any dinner. You're vegetarian.
You can't have any pudding. So who here has not seen The Wall? Who here has seen The Wall? Okay. So that's a movie. So I watched The Wall probably 200 times my senior year as an undergrad. We had it on a permanent tape loop in the lab, and we could carry on entire conversations just by quoting from The Wall. But this is one of the more famous lines. It's also from one of Floyd's songs. If you don't eat your meat, you can't have any pudding. You eat your meat might be the proposition Q, and you have any pudding might be the proposition. Eat your meat might be P. Have any pudding would be Q. Well, this is really saying not P implies not Q, right? Which is logically equivalent to Q implies P. If you're going to have any pudding, it must be that you ate your meat. And it goes on to how can you have any pudding if you don't eat your meat? And you can write that out, and you can find propositional calculus in Roger Waters' lyrics this way. But it's imperfect because it's English again, right? So, all right, so we got about 2 minutes left. Let me just put up the truth table for a biconditional, and we'll leave it at that for now. So P and Q. So the conditional P implies Q. This is always true except when the hypothesis is true and the conclusion is false, because that's saying exactly the opposite of what if P then Q says, right? Because P is true but Q fails to be true. So that's P arrow Q. If we look at the converse, Q arrow P, that looks like this. It's true except when Q is true and P is false. Now if we take the conjunction of those, which is the biconditional, that's just the conjunction of these two columns. We get that.
Can you write it out either way?
Can you what?
Like the longer way or the shorter way?
Yeah, it's usually better to do this, but when you're developing it, you might write it out like that. They mean exactly the same thing. And this is a truth table for an exclusive NOR. So if and only if is kind of the same as an X NOR, which is a little bit weird, but not a bad thing. All right, so we'll start playing with this more on Wednesday. We'll start looking at identities and more ways to create new propositions from old. Yeah?
Okay, so The Wall is a song, but it's also a movie.
The Wall is a movie,
Because I know the song.
and it's an
And
album.
the song is also. Wait, there's a movie that goes along with the album?
Yeah.
Whoa.
Yeah. Okay.
Why don't you brackets instead of the one?